So we'll have some non-homogeneous linear DE. Again, with constant coefficients, I'm not going to write that out. Something like, I don't know, maybe y double prime minus, let's go with 6y prime plus 8y equals 3e to the x plus 5x plus 2 plus cosine of x. So what makes this non-homogeneous is this side over here ain't 0. That's not 0. So the way we solve this is first, it's a two-step process. Step 1, solve the homogeneous version. So solve the left-hand side equal to 0 and get the complementary function. Get what's called YC, the solution to the homogeneous version. Then step 2, find any particular solution to the actual DE and tack it on to the end. So that particular solution we're going to call Y sub P. Now it's a particular solution. It doesn't have any constants of integration in it. It won't have any C's in it. It would just be an actual solution that solves the entire thing. Then our general solution will be y equals the sum of those two, yc plus yp. Now, when we say particular solution, we really mean something that solves the entire thing, but we're actually allowed, because of linearity, to break this up. So in this case, notice I could really call these 3 different functions if I wanted to. So I could call this, I don't know, g1 of x, g2 of x, and g3 of x. So we're allowed to, it turns out, find those particular solution pieces one at a time and just tack it all together. So we can find, say, yp1 that would solve, it would be a solution to y double prime minus 6y prime plus 8y equals 3e to the x. So only deal with the first part, find that particular solution. Same thing for this guy, same thing for that guy, and then tack it all together. So we could say this is really yc plus those 3 particular solutions, because we kind of thought of this as 3 separate functions added together. We could even call it 4 functions if we wanted to. We could call 5x 1 and 2 another function, but it's probably easier to squish those together into 1. Now, here's the hard part. How do we find these particular solutions? We know how to find that complementary function. We know how to solve homogeneous DEs with constant coefficients. How do we find these? We guess. It's literally guess and check. It's called undetermined coefficients. Undetermined coefficients. And it's really guess that that particular solution looks like some kind of function that you're dealing with, or its antiderivatives. Because remember, we're saying that when I take 2 derivatives of a function plus the derivative plus the original, I get something that maybe looks like cosine. Well, whose derivatives could give us cosine? Sines. So our YP will look like our G's and or its antiderivatives. Okay, so let's do a concrete example. Like we'll go through and we'll do this entire thing, but I'm going to do it one piece at a time. So let me write that guy up here at the top. What did I have to now? I don't remember. 3e to the x plus, I think it was 5x minus 2 plus cosine of x. So I'm going to deal with this one step at a time. Step one, find the complementary function. Find yc. So forget about all this stuff. Make the right-hand side equal to 0. Now we should have done enough of those that we can immediately write down the characteristic polynomial, which in this case will be lambda squared minus 6 lambda plus 8 equals 0. That factors lambda minus 4, lambda minus 2 equals 0. So we get lambda equals 4 and 2. And my complementary function then, yc, will be c1 e to the 4x plus c2 e to the 2x. So that's step one. Find the solution to the left-hand side equals 0. That's going to be part of our general solution. Okay, now we want to deal with this guy one piece at a time. So let's deal with the 3e to the x. So I'm trying to just find any particular solution. Anything that works will work. So I'm going to just guess, literally, this is like a guess and check, that my solution, let's call him yp1, is some a e to the x. And this is why this is called undetermined coefficients. I need to determine that coefficient, a. So let's plug it in and see what happens. His derivative would be a e to the x. His second derivative would also be a e to the x. Notice, by the way, this is important. Yeah, this is a good time to bring it up. Notice I've already used up e to the 4x and e to the 2x. I've already used those two up, and we need all our solutions to be linearly independent. So I need to make sure this guy is independent from those. If this had been an e to the 2x, I've already used up e to the 2x. This wouldn't work anymore. That would be part of the complementary function. So just like we did in repeated roots, we'd have to tack on an extra x. So if I had had a 2x up here, then this wouldn't work at all. I would need to tack on that extra x there, ax e to the 2x. But I have not used up e to the x yet, so I'm free to use it. Okay, now let's solve for a. So I'm literally just plugging these three things in up here. A e to the x minus 6 a e to the x plus 8 times the original. These are all the same. Must equal 3e to the x. So that's 1, 9 minus 3. Oh, wow, we get a equals 1. That's purely coincidence. Right? I think we get 3a e to the x equals 3e to the x. So a must be 1. Again, that's coincidence that we got 1. I literally just made numbers up. So my first particular solution is just 1 e to the x. No constants of integration on the particular solution. Okay, now let's deal with the 5x minus 2. So G2 is 5x minus 2. So I want some function here that when I take two derivatives of it, is still going to give me a linear function. So I need to kind of think backwards and think, well, what kind of function could I have so that when I take two derivatives of it, I still get a linear function? Well, then just raise the exponent up twice. Our yp2 then might be a cubic. So ax cubed plus bx squared plus cx plus d. And we're going to see some of these are 0. Now, I don't want you to stress about this. I used to stress about this. 5 minutes ago, I used up the letter A when I was solving for this guy. And you might feel weird using the letter A when you already have it, meaning we already wrote A equals 1 a minute ago. That's all right. We've moved on. We're working on a different problem. We're free to reuse that letter if we want to. Don't stress about that. Okay, so let's play this whole game. Take the first derivative. That'll be 3a x squared. I shouldn't have picked such a big one. 2bx plus c and y double prime. Take that guy's derivative, 6ax plus 2b. All of this needs to satisfy this equation. So let's plug everything in. Y double prime minus 6 times y prime, so 6 times this guy, plus 8 times the original, should equal 5x minus 2. Now, the only way two polynomials, two cubics, can be equal is if every coefficient is equal. So this is a lot like partial fractions. We got to clean all this up, gather all our cubic terms together, all our squared terms, and so forth, and see how many we have here, how many we have here. So let's look at the x cubes. So just scanning through here, that's the only x cube I have. 8a x cubed. Over on this side, I don't have any x cubes. So that must equal on the other side 0 x cubed, which means a equals 0. Meaning we didn't have to go cubic. Maybe quadratic would have been good enough. And actually linear would have been good enough. We'll see that in a minute. Gather all our squared terms together. Okay, we already said a equals 0, so I don't need to worry about that one. I've got a squared term right there. So 8bx squared must equal over on the other side. I don't have any squared terms. There's no x squared over here, so that must be 0 x squareds, which means b also equals 0. So we didn't need these two terms. We could have just used a line, but we weren't sure. I was, but I want you to see the process. Okay, then we keep going. So that's 0, that's 0. Those A and B are both 0. All we have is this over here. So let's distribute that 8. 8cx plus 8d must equal 5x minus 2. Like coefficients must be equal. 8c must be 5. Those are my x terms. So c is 5/8. And 8d must be -2. So d is -1/4. So my second particular solution, excuse me, is cx plus d, 5/8 x minus 1/4. Let's write that here. These are a lot of work, as you can see.
Sir?
Yes.
That second term in the long line, the -6 times 3a x squared plus 2bx, are we negating the c that's in that?
Oh, wow. Thank you. Thank you. You absolutely missed that right there. We do need that, don't we? Yeah. Yeah, because if we had just chosen, instead of going all the way up to cubic, a linear, then the first derivative would have been c, and that would have gone in there. So yeah, all of this is wrong. Thank you. Good catch. Extra credit point. All right, so what do we have then? -6c plus 8d. Those are my two linear terms, must equal -2. And my only, or those were my constant terms, my only term with an x is still 8c equals 5. So c was 5/8. Now we have to solve for d. So -48/5. You guys check my arithmetic here. 8d equals -2. So I'm just going to call that -10/5. Move that guy over. So it'd be plus 48. So 8d equals +38/5. So d is 38/40. Let's see, 4 doesn't go into him. So 19/20. Okay, I think that's right. We're going to type this into Wolfram Alpha at the end, and we'll check and see if I got all those constants right. All right, now we deal with that last guy, that cosine. Again, we can deal with these one at a time. So G3 is cosine of x. Now we're looking for something. This one, it does matter. Something where you take two derivatives and you get cosine, or one derivative and get the cosine. So we're going to need sines and cosines. So YP3 is going to be, again, I'm going to reuse the letters A and B because I've moved on. Let's say a sine plus a B times a cosine. Anything when I do this kind of operation on it might give me some cosine. And you might think, but there's no sine over here. The sines are going to cancel out. We'll force them to cancel out. So the first derivative is, what is it? A cosine minus B sine. And the second derivative be negative A sine minus B cosine. All right, let's plug all that in. So negative A sine minus B cos. I'm going to go ahead and distribute this 6 as I go. So -6 times this guy. -6 A cos minus 6B sine. You guys watch me as I go here. Plus 8 of those. Should equal just 1 cos. And now let's gather everybody up.
Sorry?
Yeah.
You're multiplying -6 by that first derivative of y?
Yeah.
Shouldn't that -6a cosine x be added to 6b sine x? Because that's already a minus b sine x.
So that should be a plus right there?
Yeah, I
okay.
think.
Yep.
-6 times negative b sine x.
Yep. Okay, cool. Good catch. Okay, does anything just cancel? I don't think so. Let's gather all our signs together. I've got a -a, a 6b, an 8a. So that would just be 7a. So I got that guy. I don't want to lose anybody. And then with the cosines, I've got a -b and an 8b, so 7b minus 6a. And that should just equal cosine. So all of this has to equal 0, and that has to equal 1. There's only one cosine over there. So we get this system of equations, 6b plus 7a equals 0 because there are no signs. And let's put it in the same order. Oh, it is 7b minus 6a equals 1. Now, you guys are in DE right now. I don't need to see you work out. This I would want to see. This is differential equations. This is calculus. That everything we've written so far was important. I don't need to see you work out a system of equations. You can use your calculator. You can literally type this into Wolfram Alpha and it'll solve it. So let me show you a couple ways to solve this system of equations. Now, sometimes you start typing A's and B's into Wolfram Alpha and it might not work. So I might want to use X and Y, but it will probably work like this. So I'm going to use little just because I'm lazy. 6b plus 7 little a equals 0, comma 7b minus 6a equals 1. I think is what we had. Yeah. And it solved it. You can also do this on your calculator. So let me write that down. So YP3, let's see, A went in front of sine, -6/85. 6/85 sine, and then 7/85 cosine. Okay, so let me finish writing up the general solution, and then I'll show you another way to solve that using your calculator. And then we'll check our general solution. Okay, so our general solution, y, is the complementary plus all of those particular solutions. Remember, only the complementary has any constants in it, any c's. So where were we? C2, e to the 2x plus e to the x. It takes almost as long to write all this out. Now I can't read my writing. I think that was a 7/85. I still have it on my screen. Yeah, cosine. Okay, now it is perfectly fine. There is nothing wrong with you checking your solutions in this class in a tool like Wolfram Alpha. So What I don't want you to do is go here, see what the answer is, and then just write it down without showing any work. I wouldn't give you credit for that. Oh, that's y prime. Plus 5x is 2 plus cosine of x. And it should be able to solve this. Do we have a 7/32? We had a 5. I had a 19/20. So I made an arithmetic mistake when I was finding this part right here. You guys can go through and catch my mistake. Something went wrong there because we didn't have any other constants here that would add together to get that. But this is why it's okay to use this tool. You go through all the work, you check it, and you go, oh crap, I messed up something. Let me find my mistake, and then you fix it. Okay, let me show you how to do this system on your calculator. So we can build what's called the augmented matrix. So I want to turn this into a 2x3 matrix, 6, 7, 0, 7, negative 6, 1. So I took the answer vector over here and tacked it onto the end of my coefficient matrix from here. And let me pull up my calculator. Oh, I already have it open. Okay, so we can come here into matrix, second matrix. I'm going to go into edit. It is a 3x4. So make sure you get your dimensions. It's always row by column. Type in all my coefficients, 6, 7, 0. Oh, I lied. It's not a 3x4, it's a 2x3. Something wasn't right there, was it? 2x3. 2 rows by 3 columns. 6, 7, 0. 7, negative 6. Remember, this is your negative button. 1. And then I have a tendency when I'm in here editing a matrix to type something and screw up my matrix. So as soon as I type it in, I get out of there, and then I like to check it. So I'll come back in here to matrix, grab matrix A, and just look at it and make sure it's right. And it is. Okay, now we can perform operations on it. So we come back into matrix and we go to math. And we go down to row reduced echelon form, RREF. And on some calculators, you can just type the letter A now, because we have letters in here. Notice all the green, like right there is a green A. If I do alpha A, that won't work on this calculator. Matrix A has these brackets around it. So I have to do math, row reduced echelon form, RREF. And I have to come back into matrix and grab matrix A. Close my parenthesis. And there it is, as decimals. I don't know if you guys know this, but you have an into fraction button. I can come here and hit math, and it's just number 1 into fraction. Then it'll spit that into fractions. And here are your solutions. There's your first guy, whoever you had first. I had B first in mine, and then A. So we had B in the first column, A in the second. And those are the same answers we got. Okay, so let's say we were solving this over here. you should be able to quickly see that your complementary function is going to be C1 e to the 3x plus C2 e to the 5x. Because my characteristic polynomial is lambda squared minus 8 lambda plus 15. You set that equal to 0, you get 3 and 5. So that's my setting this guy equal to 0 and solving solution. So I've already used up e to the 3x right there. So I can't do this. If I try yp1 equals a e to the 3x, if I plug that in here, I'm going to get 0. That's one of these guys. So it's impossible to get this. So what you have to do is, just like we did with repeated roots, tack on an extra x. So you'd use this, and then you'd have to use product rule to get the first derivative, probably 2 product rules to get the second derivative, and then solve. So it's a little more work.